Welcome everybody to this class of control of linear systems. This class is providing the context of mechanical engineering for INSA Lyon in the third year. It kind of continues the class on sensor and signal processing of the first semesters, and it opens the way for coming classes in the fourth semester, especially if you have chosen the mechatronics path. So what is it about? We are going to see shortly. It is mainly about control on and regulation of devices. What I mean by device, anything you might create, you might figure out, needs to be controlled, needs to have a program, if you want, a software which tells it how to behave properly. You just don't just need to build the car, you also need to control the car and drive it safely everywhere. And if you do this by automation, by an automatic device, this is the context of automatic control, which we are going to discover here. This class is a very basic introductory class, like many other are taught everywhere in the world, and it will give you the basic introduction to this topic. So, course schedule this year is going to be a little bit strange with respect to the other year, so we try to provide you the maximum of information online. Basically, there are 6 lectures and 12 tutorials, and the planning of the tutorial has been published. So basically, the tutorials are up to you to do and correct, and you will have the possibility to ask questions to the teachers in a way that will be provided. You will be specified you by the teacher themselves. Course material, you have lecture notes in French, but you can just look at the slide, they should be enough. And there is a tutorial booklet both in English and French with solutions. And look on Moodle page also, you'll find a lot of information, and we are going to update it as soon as we have new stuff, so please keep an eye on that. Concerning these lectures here, so these lectures I try to provide you a little bit more than only the slide, so you have the comment, the voice comment, which probably helps. It is not the same as a real class, in the sense that I will try to keep it as compact as possible, so that the video is short enough and doesn't take you too much time. In a normal class, I would use repetition and try to hammer in your head the most important concepts. I will not do it here, because you have the freedom every time you like to stop the video and go back and listen to it again. So please do it. If you need, take the time to listen again what I said, and take the time to stop the video and read the slide in detail and make sure you understand. So what is automatic control? You can read it here. All the methods allowing the analysis and the enhancement of the dynamical behavior of a system without human intervention. That's what I try to say. Imagine you want to drive a car. You can do it by human, or you can do it with an automatic car. So this is the topic of automatic control. So you can, as a result, replace human in annoying repetitive tasks, but also be better than human. So instead of having a worker, you can put a robot, as you see, and this has a great enhancement effect in factories and in industries. So this either increases the profitability of the industry and the precision, the reliability, etc., etc. And you can also have a look at assembly lines and warehouses as examples of this. And then other examples still in the industry, you can just go into YouTube and have a look at all these amazing things you can find, like automatic cars or robots. You can have all kinds of applications in countless of industrial fields, and even more dreaming application, like you cannot send humans to Mars, you can send robots. So these robots have to be automated, or same other dangerous places like inspection, nuclear plants, or bomb defusing, etc., etc. So let's go to the origins of automatic control. The birth of automatic control coincides basically with the development of the steam engine. And the first automatic control device was not an electronic device, it was a mechanical device. This one you can see in the picture. It's called the centrifugal governor. You can click in the link I provided here to have a little video that shows you what it was about. Basically, its goal was to control the speed of a steam engine shaft, the angular velocity of a steam engine shaft. So the idea is simply that if this shaft is connected to two flywheels, say two balls, as you can see, which are free to rotate, if the shaft turns too fast, these balls will go far from the shaft itself, and so with the mechanism this could be connected to the valve of the steam, and this would, if too fast speed would close the valve, you could imagine that the shaft would slow down, and the other way around, if the shaft turns too slow, then you would have the balls getting closer to the shaft, and the valve would open up. So it makes sense. If it goes too fast, you close a little bit the valve, so it will slow down. If it goes too slow, you will open it up a little bit and it will go faster. And actually what they found out is that it didn't really work that way, and there were some problems that they didn't forecast, in the sense that instead of settling down to the desired velocity, the steam engine would just accelerate and decelerate and accelerate again and never settle down to a stable position, let's say. So this was the case study which stimulated the first scientists to get deeper into the mathematics of control. I really invite you to click on the video and have a look at the animation of this flywheel governor. So, as I said, applications are countless. You can just get inspired here by the list. And now we move on to the more mathematical and say hands-on stuff part. So basically what we need to do when working in control engineering, we need to deal with signals. What's a signal? Is a function of one or more variables associated to some physical phenomenon. I think everybody's familiar with a signal. So you can have like a signal function of time, the first one there. What is it? The time signal. It could be anything that changes with time. You can have a space signal, like for example, function depending on two coordinates. An image is a typical example of a space signal. Or you can have a space temporal signal, like a video, something that changes in space and time. In this class, we focus on continuous time signals, as you can see here. Continuous time signals are functions of time, and time is continuous variable. And what actually we focus on is on the cause and effect links between signals. Because one signal could be the effect of another signal, which is the cause. So we call a system such kind of causal relationship. So a system is any stuff, let's say, which establishes a relationship between some input signals, cause, and some output signals, effects. So you can imagine it like an input signal goes into a system, and the system will provide, as a function of this input signal, some output signal. And a system is always part of an environment, and so there will be multiple systems interacting in most of cases. And also, considering the inputs themselves, in most cases we can distinguish two types of inputs. Inputs which are out of our control, which we call disturbances, and inputs which are in our control, which we can determine, and we will call these control inputs. So let's look at this picture here, which provides more or less a visual description of what I just said. And this is a typical block scheme employed in most cases in control engineering. So the first case, you can see you have one input and one output, and several disturbances, this kind of signals, the systems, are called SISO, which means single input, single output. Or you can have multiple input and multiple output. Let's see some examples of what system can be. So, in case of an electrical system, you might have a simple filter like the one shown here. You have an input voltage, VE, and you have an output voltage, Vs. And the filter determines the relationship between the signal Vs and the signal VE. VE can be anything, comes from outside, but Vs will depend on VE and on the filter itself. Let's look at a more mechanical example. Consider a car. What are the inputs of the car? The control inputs are gas pedal, brake pedal, steering wheel, etc. What are the disturbances? Well, whatever you cannot control directly, wind, traffic, road conditions, etc. And what is the output? Well, the speed of the car, the location of the car, etc., etc. So, imagine you want to drive this car now. Imagine the road is straight, there is no wind, there are no other cars, no traffic, etc., etc. In principle, you might just orient the steering wheel and then keep the gas pedal down and go straight without even looking at the road. This is what we call an open loop control. What it means, open loop control? You don't look at the output. You don't look at your speed, you don't look at where you are in the car. If you are lucky enough and you know your car very well and all the external conditions, well, you can drive on your road without looking. Of course, as you might understand, this is not very safe, especially if you have disturbances. Imagine you have wind, imagine you have other cars, the road is not perfect. So what happens? Can you really drive a car without looking? No, you cannot. You need to correct, in fact, your action as a function of what you see outside. And this is what we call a closed loop control. Control taking into account what happens, taking into account your measurements. So in general, a closed loop control takes this shape, this scheme. You can look at the example of the car, of the driver driving the car. You get a reference, say a goal, which is compared into your brain from what you see, and you look at the road. Then the brain will act on your muscles, steer the car. The car is also subject to the external disturbances, and then the result will go through your senses, will go through your eyesight, and you can use the output of the senses to correct your action. This is a typical closed loop control scheme, which generalizes into this for any situation different than the car. You have a goal, and you have a first logic, let's say, called controller, which compares the goal and the measurement. Then you have an action required to some power delivery system, which acts on the system itself, the car, for example. And then the result of the system goes into some sensor, and the sensor provides useful information for the controller. So in this slide you can see how we call all these elements. So the goal is called the set point, for example, the imagine for the car, the speed at which you want to go. The difference between the speed that you want and the measured speed is called the error. The controller works trying to bring this error down, so it looks at the error and then decides a control action. So basically how we have to act on the gas pedal. Then the gas pedal is the tool which brings the power to the engine, and it provides a physical input to the process, to the car. So engine speeding up or down. The engine also influenced by the external situation, so wind, whatever. And then we have the speed of the car, which is measured by a sensor and provided back to the controller. So the goal of this class is to give you some hints, some ideas of how to have a general procedure for designing a control system. So you have probably some specification of what you want to obtain. Then we have to analyze the system that you want to control. And then the key part is determine a control law, which means what we put inside that controller box, which might be a computer, an analog device, or even a mechanical device, as we have seen for the flywheel regulator example. And then, of course, we need to be able to validate the result of this procedure. So, what kind of specification you might have? Well, there are several objectives you might have when you want to steer a system. We can distinguish mainly two. You might have two main goals which can appear at the same time. The first, we call it trajectory tracking. As we said, you have a set point for one of your variables of your system, like speed of car. You want to set the speed. So you would like your car to follow exactly the speed that is imposed. The second kind of specification is what we call disturbance injection. So it means that basically we want to make sure that the system behaves regardless of the disturbance. So you might think that, keeping again the example of the speed of the car, your car keeps the speed even if there is a wind outside or the road slopes up or down, etc. Concerning the analysis, we have surely to understand which are the signals that are involved in any system, and the first important thing to understand is to distinguish them as inputs and outputs, and each of these inputs have to be classified as controls or disturbances. And the outputs, you might have outputs that are measured by sensor, so they are visible or not measured at all, but still they might be important. Then what is key is to find a mathematical model characterizing the relationship between these signals. So how the outputs are determined by the input. And this can be done basically by either the laws of physics or from experiment. And then study of the characteristic of the system will help the development of the mathematical model. This is also called study of performance. Synthesis and validation of control law. Based on the analysis of the system, you should be able to choose the kind of control device and the law and tune the parameters that provide the desired behavior. Once this is done, one can perform a simulation with some software to forecast what is going to happen, and then of course the last step is to realize the system and test it in the reality before production in mass scale, let's say. So this is what is going to come for the rest of this class. We have to review a little bit the mathematical tools, then we'll go into modelings of systems, representation of systems with some nice graphical tools. Then we go to the problem of stability, which probably you have already seen in the classes of mechanics. And then we'll go to the performance and synthesis of control law.